So, Kevin, you said you've watched a few of these. I'll give you a little introduction, and then we're good.
Sounds good.
Great. Okay. Are you ready? Good. All right. I'll start recording. Okay. So welcome back to another seminar, everyone. It's our pleasure to host Dr. Kevin Carlberg today. So this is falling outside of our regular schedule. Unfortunately, we had to reschedule, but we're very, very happy that people were able to make it for the talk today. And we are very excited to have Dr. Carlberg with us. So just a brief introduction. Dr. Carlberg is an AI research science manager at Facebook Reality Labs and an affiliate associate professor of applied mathematics and mechanical engineering at the University of Washington. So he leads a research team focused on enabling the future of augmented and virtual reality through AI-driven innovations. His individual research combines concepts from machine learning, computational physics, and high-performance computing to drastically reduce the cost of simulating nonlinear dynamical systems at extreme scale. Previously, Dr. Carlberg was a distinguished member of technical staff at Sandia National Laboratories in Livermore, California, where he led a research group of PhD students, postdocs, and technical staff in applying these techniques to a range of national security applications in mechanical and aerospace engineering. So I think I speak for all of us when I say I'm very excited to hear what Dr. Carlberg has to tell us today. So without further delay, I turn it over to you, Dr. Carlberg.
Thank you very much, Jason. And just a quick disclaimer at the top here, even though I do work at Facebook, none of this work is Facebook related work, and I am not representing the opinions or perspectives of Facebook in any way over the next 60 minutes. So with that out of the way, what I'm going to be discussing today is work that I've done over the past decade in the theme of AI for computational physics. And that's a pretty broad umbrella in terms of a topic. But what we're going to be honing in on is basically applying AI techniques to enable real-time high-fidelity simulation of complex engineering systems. And so some of the people in this call, I see Linda and I saw Sophie Glass also. This is actually what we're getting at here is nonlinear model reduction. That is applying various projection schemes with manifolds learned from deep learning to reduce the dimensionality and complexity of simulating dynamical systems. So I just want to quickly call out that a lot of the work that I'm going to be presenting today was done primarily by my former postdocs, Kuk-Jin Lee and Eric Parrish, who are currently at Sandia National Labs. Okay, so what's the motivation for this work? So as I'm sure many folks on the call here are well aware, high fidelity physics-based modeling and simulation has become indispensable across a wide range of applications in science, engineering, and entertainment, as it provides a mechanism for accurately simulating the realistic performance of complex engineered systems, the performance of autonomous agents, and the physical movement of virtual characters in films, for example, and as we hope to do one day in virtual reality, interactions with virtual objects. As such, physics-based simulation not only plays a crucial role in national security work done at my previous employer at Sandia, but also plays a surprisingly large role in the world of virtual and augmented reality. However, as we rely more and more on these simulations for a range of critical applications, greater demands are being placed on their fidelity. And to ensure these models have high predictive fidelity, we must imbue them with very fine spatiotemporal resolution, which leads to computational models that correspond to extreme scale nonlinear dynamical systems. And as you might expect, the extreme scale nature of these dynamical system models incurs a very high computational cost, which precludes them from being used for a range of very important time-critical problems that we would like to use them for, like model predictive control and engineering, health monitoring, interactive virtual environments in VR and AR, as well as design optimization. So the overarching goal of my work really here is to leverage methods from AI, dimensionality reduction, and model reduction to break this barrier so that we can actually use these high fidelity predictive models for a range of these very important time critical problems. Because to date, these high fidelity models have been used primarily for cases where we can afford on the order of a handful or maybe 10 simulations. So what's one example of this? So one example I previously worked on at Sandia is modeling the what's called the internal captive carry problem. Basically, this was work done by Matthew Baroni and Srini Urdhajenison. And the idea here is we want to simulate the pressure exerted in a store when it's immersed in a three-dimensional cavity. And so the engineers over at Sandia put a lot of work into developing a very high fidelity model that is both validated and predictive in that it matches wind tunnel experiments to within 5%. And I won't go into too many details here on the actual model. On the left, we have our structural dynamics model. And on the right, we have a two-dimensional slice through that three-dimensional cavity where I'm visualizing the gradient of the density. In order to achieve this predictive fidelity, the dominant cost in the simulation is really the fluid dynamics simulation, which is characterized by 100 million cells and 200,000 time steps. So just a single one of these simulations incurs 5 weeks on 5,000 computing cores, which leads to an obvious computational barrier that prevents us from using this model for a range of important time-critical problems in aerospace engineering, like exploring the flight envelope, performing uncertainty quantification, doing model predictive control, and ultimately doing robust stochastic design of the store and cavity. So this is just one illustrative example. Of course, you can imagine many other cases where analysts build very highly predictive models that are too expensive to run in real time. And so this actually was articulated a few years ago in what you might have seen put out it was mentioned in the New York Times, among other publications, that NASA issued a high performance fast computing challenge where they articulated this computational barrier quite nicely. So they stated that despite tremendous progress made in the last few decades, CFD tools are too slow for simulating complex geometry flows taking from thousands to millions of core hours. And the example I just showed on the last slide was 5 million core hours. So it's sort of right in the wheelhouse of what NASA is looking into in terms of the scale of the problem they're looking to address. And what they articulate is to enable high fidelity CFD for multidisciplinary analysis and design, the speed of computation must be increased by orders of magnitude. And they call out a desired outcome of accelerating these calculations by between 1 and 3 orders of magnitude. And over the next sort of 45 minutes, I'm going to hope to show you and convince you that, that the work that we've done actually gets at this exactly. We achieved nearly 3 orders of magnitude computational cost reduction by cleverly leveraging AI methods within a model reduction framework. And so we actually did submit our work to this challenge, but unfortunately they shut the challenge down right before we were about to submit because they had too many submissions. So unfortunately missed out on an opportunity to potentially win this challenge, but who knows. Okay, so anyway, so let's take a step back and think about how we might tackle this problem in a fully general expressive way. So the model that we're going to use and consider to be our high fidelity model throughout this talk is simply a parameterized nonlinear dynamical system, where if we have a PDE, we imagine that we've already semi-discretized the PDE in space, leading to this large-scale system of nonlinear ODEs. So X here is our state vector. Imagine this is a vector of length, say 100 million. F is our velocity vector, which we assume to be nonlinear in the state. Mu denote parameters. Each instance of these parameters defines a new initial value problem. We have some parameterized initial condition, and we're going to simulate in some finite time window. And so what are we going to consider to be a time-critical problem in our context? Basically, what we would like to do is rapidly solve this ODE for many different points in this design space that we're going to denote by D query, all these blue points. And rapidity here is defined by some wall time or core hour threshold that we're going to enforce our simulation to be below. And so how might we tackle this problem? Basically, the main idea that we're going to pursue in line with traditional machine learning approaches is we're going to collect simulation data that's very expensive just by simulating this model, the original high fidelity model, at a handful of points shown in red here. And then we're going to exploit that data to somehow reduce the cost of solving this system at the remaining query points. In a sort of many query scenario, the idea is we can amortize the cost of training over many subsequent queries that are fast. And if we're in a real-time deployed setting, the idea is we can do all of the training and learning in sort of an offline stage. And then at inference time, we can run the model very quickly. And so I'll make one quick note here. Because we're adopting this general mathematical formulation, it does preclude us sort of a priori from doing anything that preserves structure that's particular to specific dynamical systems. So a little bit later on, I'll dive into the structure of this ODE for a particular class of problems and explain how we can imbue our reduced order models with specialized physical structure that we want to preserve. Anyway, so all the methods I'm going to propose today and discuss follow the same sort of 3 classical steps for machine learning. One is training, which I just mentioned. We're going to collect data. In our case, this corresponds to simulation data that we collect simply by running our high fidelity model at some number of points detraining. Number two, we're going to apply various machine learning methods to basically identify important structure that we can exploit in the data. We'll apply sort of a variety of both unsupervised and supervised methods for this purpose, and I'll go into details there a little bit later. And then once we've identified the structure, the idea is we then, in step three, perform inference. That is, we reduce the dimensionality and complexity of this model and run our simulation at the remaining points that we care about. So before getting into what we did, I will first kind of walk through what these steps look like for a classical method known as POD-Galerkin. I'm sure many folks here are familiar. I know Linda wrote one of the sort of seminal papers on this back in 2003. But I'll sort of walk through what these steps look like in this framing for classical POD-Galerkin. So the idea of POD-Galerkin is step one is training. So what this means is we take our ODE, we pick one point in parameter space, which associates with one instance of our parameters mu. And then we run a transient dynamic simulation, meaning that we integrate this ODE in time. And we're going to say that each time step, or maybe we skip a few time steps, but that's not really central to the methodology. We save our state vector x at every time instance that we care about, which lead and concatenate these all together into an n by t matrix, where n is the dimension of our state. Let's say that, again, this is 100 million, and t is our number of time steps. Say that's on the order of 10,000. So we form this n by t matrix, and we then repeat this sort of training procedure at different points in parameter space, where these points are chosen in some clever way, perhaps via space filling design of experiments. What we then do is take this data and we view it from the machine learning viewpoint as comprising IID samples of a spatially distributed vector, or of a spatially distributed solution variable. This is not strictly a correct interpretation when you think about principal component analysis, but it's what's commonly done in POD. And some of our other work actually exploits the space-time structure of this data that I'm not going to talk about today. So anyway, let's assume that we can that we view these as IID samples of our underlying solution. We then apply PCA to this, which essentially means we compute the singular value decomposition, and we truncate the left singular vectors, preserving only the dominant modes. And in our community, this is known as POD, but of course, in machine learning, it's PCA with a few slight changes in the algorithm. But basically, you can think of these vectors, the columns of phi, as the principal components of the spatially laid out simulation data. So in POD-Galerkin, the third step is reduction, which is that we want to reduce the cost of solving the ODE for all remaining points in parameter space. And the way that this is done is we take this basis, we then enforce our solution x to be approximated as some proxy state x tilde of the same dimension, which we enforce to live in the space spanned by the columns of phi. So in essence, we're introducing a low dimensional linear subspace of our original state space Rn. And so we imagine the number of columns in phi we'll call that p, and let's say p is on the order of 10 or 100. So if we do this, there's sort of two ways of reasoning about projection. One is the classical Galerkin method, and the other is what we kind of came up with about 10 years ago now, which is known as the least squares Petrov-Galerkin method. So how do these two methods work in sort of a general setting? We take our high fidelity model that I showed earlier. I'm going to suppress dependence on mu for notational convenience. And then we write the ODE residual, which is just basically the misfit of the left and right hand sides of this ODE, right? And so what Galerkin projection does is it introduces this kinematic approximation shown in the top left and minimizes the ODE residual over that subspace. So in essence, what POD-Galerkin does is it says, I'm going to compute the velocity vector at each instance as the minimizer of the time continuous residual over the linear subspace spanned by the columns of phi. So because phi is an orthogonal matrix, you can convince yourself that these are equivalent statements. However, we know that to actually compute a discrete solution for either of these time continuous models, we must introduce a time discretization method. We're going to consider, just for simplicity here, linear multi-step schemes, but we've also looked into this for Runge-Kutta schemes. And if we do this, what we come up with is what we call an O delta E, which is a fully discrete system of, if it's implicit, nonlinear algebraic equations that we solve at each time step. And so we get that for the full order model in the center here, and then the Galerkin ROM on the right. And the reason that I have colored that bottom right box red is because it's to denote the lack of optimality we have at the time discrete level. As we showed in some of our papers, even though the Galerkin ROM exhibits optimality in a least squares residual minimizing sense at the time continuous level, right? It clearly minimizes this L2 norm of the residual. Once you introduce time discretization, you can't in general show that the discrete sequence of solutions you compute associates with a solution to any optimization problem. So any notion of optimality we had at the time continuous level is actually lost at the time discrete level. And what we showed over, course of a few years is that this causes significant problems when you actually apply it to stiff ODEs like turbulence, for example. And so what we propose is an alternative ordering of discretization and projection, where rather than projecting the time continuous ODE, we project the time discrete O delta E, and compute the sequence of solutions that minimizes that discrete residual over the linear subspace. And this is what we call least squares Petrov-Galerkin, because if you write out sort of the necessary optimality conditions here, you can show that it associates with a Petrov-Galerkin projection onto phi with the residual orthogonal to the Jacobian of the residual times phi. And I'll point out there's a few other residual minimizing reduced order models that have been pursued. Recent work I did with Eric Parrish actually shows how you can extend this residual minimizing formulation to arbitrary projections in both space and time. So that's a pretty interesting paper that I don't have time to discuss today. Okay, so let's see how this actually works on this example I sort of teased earlier, this so-called captive carry problem. So I'll consider a slightly simplified version of this, where we solve the unsteady Navier-Stokes equations, Reynolds number 6 million, a Mach number of 0.6, about 1 million degrees of freedom in my spatial discretization, and about 10,000 time instances in my temporal discretization. So what we do is we take this model, and then we're going to apply our LSPG model to this. And so if you recall, basically what I'm solving at each time step is this time discrete residual minimization problem. However, if you're a numerical analyst, you'll immediately see that even though the subspace that we're computing the solution over is low dimensional, right? We're only computing on the order of 100 scalars here, because x hat is a low dimensional vector. I'm doing that by minimizing the sum of squares of, in this case, 1 million residual elements, right? So the computational complexity of solving each least squares problem at each time step is going to scale linearly with the original dimension of the problem. So this will preclude us in general from achieving n-independent operation counts in real-time simulations. So what we do to sort of overcome this is we replace the Euclidean L2 norm here with a data-driven semi-norm, which is a semi-norm over the full space, but is actually a bona fide real norm over the low dimensional subspace that we're employing. And so the way that we learn this semi-norm is basically in a data-driven manner. Again, I can't get into details here, but the main idea is that it requires evaluating the residual at only a small number of points in the domain. And what we do is we train this semi-norm to be as close as possible to the real Euclidean norm over our training data, such that these norms are equivalent with constants that are close to 1. And so what this means is once we implement this model, because we only need to evaluate the residual at a small number of points, we only need to do physics-based calculations on a subset of the mesh shown in red here. And this is what we call the sample mesh approach, which allows us to do HPC caliber simulations on a laptop. And the key thing that I'm going to sort of get into more later on is if you look at this model, it's a very simple model on the top here, but it's quite interesting in that we are injecting machine learned structure through phi directly into our simulation code, because the residual here is defined just by my CFD code. So we're injecting sort of machine learning or AI driven approximations directly into our physics code and computing the element of the trial manifold that minimizes the true residual from a first principles viewpoint. So this is not a purely data-driven approach. Many of those are attractive for different reasons, but this is actually injecting directly machine learning quantities into simulation codes. And so what we obtained is a result shown here. In this case, Galerkin projection, POD Galerkin was actually unstable. And we got very good results with LSPG model reduction. So in this case, we're running in half an hour on my laptop as opposed to 5 hours on 48 cores, yielding 230x savings in core hours with sub 1% errors in the time average drag. And so based on these results now, any CFD code that you download off the internet or employ, whether it's commercial or open source, has LSPG as sort of the backbone simulation capability for all the simulations you run. That's actually not true, right? So if you know CFD, you know that this is actually not a commonly used method in practice. And so why is that the case if these results are so cool and so exciting? And it's really because this particular example, what we're doing is we're training over a finite time window, and then we're predicting beyond that time window. But when we get into problems that are chaotic in nature, like turbulent flows, and when we get into problems that are even more advection dominated, even these methods have substantial shortcomings that we need to address. And so in this talk, I'm going to sort of describe some of the more recent work we've done that tries to overcome some of these sort of major shortcomings in linear subspace model reduction. And we're going to leverage some recent innovations from AI to do this. And so I'm going to hope to convince you that even though we're using sort of catchy terms from AI and like sort of hot methods, they're very well grounded in a strong motivation that gets at some of the core shortcomings of existing model reduction techniques. So the first shortcoming of all linear subspace methods, whether it's POD, balanced truncation, moment matching methods, is that this linear subspace approximation is extremely strong. And it's actually an inappropriate assumption in many cases. The fact that we are restricting the state to live in a low dimensional subspace that's linear is in and of itself a very strong statement to make, right? And many problems characterized by a slowly decaying Kolmogorov width, basically any advection dominated problem, will break the ability for us to generate any subspace that is a good approximation of all solutions in the manifold. And so our recent paper from last year, which I'm going to discuss first, tries to get at this directly. And it turns out this actually was the highest cited paper in computational physics of 2020, which is pretty exciting, as of now at least. The second is that important physical properties are not generally enforced by these methods. So these two projection methods that I just showed, Galerkin and LSPG, they both minimize the residual, but they don't say anything about the underlying physical properties that characterize the original simulation. So if we have Hamiltonian systems, for example, we have symplectic time evolution. If we apply finite volume techniques to conservation laws, we know that we are enforcing conservation strongly over each control volume. And there are variational principles that underpin finite element approximations, for example. And none of those are generally preserved by these types of residual minimizing techniques. And so we have a few methods. One of them recently we published in AAAI on how we can imbue structure preservation with these methods. And finally, error analysis is very difficult. So the reason I knew in the previous example that we had sub 1% errors is because I also ran the high fidelity model and compared the results. That's obviously not a practical approach. And if you're familiar with literature and model reduction, most error analysis is done from this sort of very rigorous functional analytic viewpoint of generating rigorous a posteriori and a priori error bounds. But for practical problems like the ones I'm considering here, these bounds are often very pessimistic. So, error sort of a posteriori upper bounds often overpredict the error by 3 orders of magnitude. And so an analyst can't really make use of that result and to understand the true error incurred by model reduction. So for that, we've been pursuing a variety of statistical learning methods that try to build rigorous statistical models that bake in the uncertainties and quantify the uncertainties incurred by introducing these model reduction approximations. So I will first talk about this first kind of core limitation of classical linear subspace model reduction techniques. So to understand the mathematical motivation for this, I'm going to introduce a notion of the Kolmogorov width limitation of linear subspaces. So I don't expect everyone here to know what this means, but I'm going to walk through basically, some intuition for why this is a key problem in the model reduction community. So for this, I'm going to introduce first two mathematical concepts. The first is calligraphic M here, which is just the solution manifold. So going back to our original formulation, this is merely the set of all solutions that I obtain, basically for all trajectories and all points in my parameter domain, calligraphic D. So think of this as all solutions I could ever compute for my parameterized initial value problem. I'm going to also consider SP, which is the Grassmannian. It's a set of all p-dimensional linear subspaces of Rn. So what is the Kolmogorov width of this problem? So the Kolmogorov p width is nothing more than the infomizer over all p-dimensional linear subspaces of Rn of p infinity ms, where p infinity ms is the L infinity projection error of the manifold onto that subspace. So what this basically means is if the Kolmogorov p width for a certain manifold is small, there exists some p-dimensional linear subspace that accurately represents all elements of that solution manifold, right? So what I'd like to do now is actually plot what this looks like on a sort of academic example. But to facilitate that, I'm going to replace this L infinity norm with an L2 norm because it facilitates computation, right? It's a lot easier to compute. So think of this like sort of a modified Kolmogorov width. So if I do this on an example, I'll explain what this is later on in the talk. And this is a very typical kind of exponential decay of the Kolmogorov width that you often see in many problems in science and engineering. So we see this decay as we increase P. Obviously, we know that the Kolmogorov width must decay monotonically. but we get this sort of exponential decay. So what I can do now is actually assume that I've computed some POD basis, and then compute the L2 projection error of the manifold onto that basis. And that will yield this dashed blue curve here. And what this is again, it's the L2 projection error of the solution manifold onto my POD basis. So now let's imagine that I solve so what I can do now is actually interpret the gap between these two as corresponding to the training deficiency in POD. If I had infinite training data, these would actually collapse on one another, right? Because I would by definition be computing the optimal subspace. So this gap here represents the fact that I haven't completely done a full sort of a full sampling of the manifold in my training process. What I can do now is actually solve a reduced order model with that basis using, say, the LSPG technique. And if I do that, I can compute the relative L2 error in my solution. And the gap that you're seeing here is what we can quantify and discuss as the closure error in my reduced order model. It's basically the failure of the ability of my reduced model to generate the projection of the manifold onto the subspace that I'm considering. So there are methods that have been pursued in the literature by my former postdoc, Eric Parrish, for example, that really get at this closure error term. And Trent Iliescu has also worked a lot in this area. So we can reason about those two gaps in this plot, but rarely is it asked, how good is this original exponential decay of the Kolmogorov width itself, right? It seems good, right? It's exponential decay. That sounds like it's decaying quickly. But what I'm going to argue here is that it's actually very not good at all. And that's because in this particular example, we know the underlying solution manifold is of dimension 3. And that's because we have a well-posed initial value problem with two parameters, mu1 and mu2, meaning that we know that there's a unique mapping from 3 variables, time, mu1 and mu2, to the solution vector itself, which means that time and the parameters define a parameterization of this manifold that is of at most dimension 3. So the fact that we have a substantial error when we set the linear subspace to the true manifold dimension, even for the hypothetically optimal linear subspace, the fact there's a big gap there is the Kolmogorov width limitation of linear subspaces. We can never get at 0 error with a linear subspace in general when we set the subspace dimension equal to the true manifold dimension that's underlying the problem. And so the goal of this work is to overcome this limitation via projection onto a nonlinear manifold. And sort of the promise of this approach is that we know there exists some nonlinear manifold where the error here for p equals 3 should be 0, and that's what we're going to try to target. So we are, of course, not the only ones to have looked at this problem in model reduction. There's been a lot of work that's been pursued. As of writing this paper, there were sort of 3 primary classes of methods. The first was this class of techniques that tries to still use a linear subspace, but somehow transform or update that subspace either by advecting the modes, doing a coordinate transformation, shifting the POD basis, transforming snapshots, and so on. So researchers have shown this can work much better than a fixed basis, but many of these approaches require problem-specific knowledge or characteristics. So some of these methods require knowing the advection speed at which you have to move these linear basis vectors. And in some sense, that's really not very good because you have to kind of solve the problem to know how to move your modes around. And these methods do not also consider manifolds of general nonlinear structure. And I think one can view these as really trying to solve the right problem in a kind of a fundamentally wrong way, in my view, because we're still living with this linear subspace view, and we're trying to overcome a limitation of linear subspaces without considering, just directly going for a nonlinear manifold. Number 2 is the a priori construction of local linear subspaces. So the idea here is you can actually build tailored linear subspaces for different local regions of the space-time domain or the state space. And these are also, these researchers have shown very good results here. But again, these are basically building sort of piecewise linear manifolds that are not general, that don't have general nonlinear structure. And you often get challenges when you have sort of high dimensional spaces that you're trying to decompose. So when you do this in parameter space, if you have a large number of parameters, it's really hard to come up with some kind of decomposition of that high dimensional space and build a subspace for each of those subdomains. As of the writing of this paper, there were really 3 papers that we could find that attempted to do model reduction on general nonlinear manifolds, but there were some key shortcomings of these methods. They were kinematically inconsistent, they were limited to piecewise linear manifolds, and they lacked any notion of optimality. And so the goals of this work really were, mainly twofold. The first was to overcome obvious shortcomings of existing methods. We want to ensure we can support general nonlinear structure, have kinematic consistency, and satisfy some notion of optimality. And number 2, we really want this manifold to be learned in a practical way. Ideally, it should be as pragmatic as POD, where we just take snapshots, turn some kind of crank, and get out a nonlinear manifold, right? Because many of the previous methods, you need to have a lot of specialized problem knowledge and build these sort of bespoke methods that are very tailored to a specific problem. So we would like it to be as easy to implement as POD, ideally. So for the first of these, we developed a novel family of projection methods that we call manifold Galerkin and manifold LSPG that work on basically any manifold that's written from the extrinsic view via parameterization function. So this has nothing to do with deep learning. It's only basically differential geometry and dynamical systems. And the second is via deep convolutional autoencoders. And we've actually found that using these deep convolutional autoencoders generates extremely good manifolds that are nearly perfect for some of the examples we've seen in a very turn the crank kind of way. So I'll first talk about the projection scheme, and then I'll get into how we learn the manifold. Okay, so our paper has a lot more details here. I'm just going to walk through high level intuition as to how this works. So if we view sort of classical linear subspace methods from the extrinsic view via parameterization function, you can basically write this subspace as just the set of all solutions phi x hat where x lives in Rp. And so intuitively, if n is 3 and p is 2, you get just a plane in R3, right? This is pretty obvious. If we enforce the state to live in this subspace, you can write algebraically that x is approximated by x tilde, which is equal to phi x hat. And then if we apply the chain rule, because phi is time independent and state independent, you can see that the velocity must also live in the exact same subspace as the state, right? So this is pretty straightforward. This is what's been done for, decades at this point. So if we're going to extend this to a nonlinear trial manifold, it seems obvious once you write it down, right? You basically would write this instead of a linear mapping phi, we can introduce some general nonlinear function g that maps a low dimensional vector to a high dimensional output in state space coordinates. We're going to require this to be continuously differentiable so that we can actually compute the tangent space of the manifold. And for some of the theorems that we developed, it needs to be twice continuously differentiable. But anyway, if you have n equals 3 and p equals 2, what you come up with is some nice curved manifold in R3, right? So if we enforce the state to live in this manifold, we have this algebraic expression. And then if we apply the chain rule, you can see that at every point in time, the velocity must live in the tangent space of that manifold, right? So this is the key kinematic thing that was missing in some of the other papers, is that, being just careful about ensuring that the velocity lives in the tangent space of the manifold at any point in time. So then how do we perform projection given these subspaces, right? And this is previous work had basically looked into encoder methods to define the projection. This is actually, in my view, not the right way to do it, because you can't prove in general any optimality property. So instead, we're going to peel back to what I showed earlier and try to do least squares projection onto the right kinematic approximation. So in the linear subspace case, we took this trial subspace, and Galerkin did a least squares projection onto the time continuous residual, which is associated with this projection scheme here. And LSPG did the same thing on the time discrete residual. So now, given this parameterization function g in the nonlinear manifold case, we can apply the same idea. So because we're computing the velocity, we want to introduce the tangent space of the manifold into our residual and compute the velocity that minimizes this time continuous residual over the tangent space. And you can show that this associates with a modified Galerkin projection. And the beautiful thing about this method, as shown here, is that because we're basically evolving the coordinates, the intrinsic coordinates of the manifold, integrating this with any time integrator will guarantee that the trajectory will live on the manifold. So you don't need any kind of fancy exponential or logarithmic mapping to go, to evolve on the tangent space of the manifold and then come back down. You're automatically always staying on the manifold because we're evolving the extrinsic or the intrinsic, not the extrinsic coordinates on that manifold. And then the LSPG variant of this is quite obvious as well. And so what you can see here is by adopting this and not using an encoder to define dynamics and projection, we can guarantee the satisfaction of residual minimization properties. And just as a sanity check, you can prove to yourself, and we proved in the paper, that under very modest conditions of a smooth manifold and limited variations in the generalized coordinates over time, and taking the limit as the time step goes to 0, these are actually equivalent projection schemes, the Galerkin and the LSPG. And intuitively that makes sense, because time discrete projection is equivalent to time continuous projection in the limit of everything going to the time step going to 0, assuming sufficient smoothness conditions, right? So we also derived rigorous a posteriori error bounds for this approach. over general nonlinear manifolds. It's a pretty straightforward result. So the top line here is the Galerkin approximation. The bottom line is the LSPG approximation. The rightmost term in the bound is just the recurrent term in the error bound, which is the same in both cases. And what we see here is that manifold LSPG is actually sequentially minimizing the new contribution to the error bound at every point in time, which is a nice sort of, a priori result that we have. And I'll show later on that empirically what we get is actually almost always LSPG outperforming substantially Galerkin projection. So that's just an overview of like how we do projection onto some nonlinear manifold expressed from a parameterization function. I have not yet said how we build this parameterization function. And this is where we're going to get into deep learning methods. Okay, so how do we apply this and how do we build this manifold up? And we're going to use, as I mentioned and alluded to, deep convolutional autoencoders for this purpose. And so one key thing when you look into the literature on learning, on sort of manifold learning or nonlinear embedding methods in AI, you see that like a lot of these methods actually just provide the mapping from the high to the low dimensional space. So methods like isomap, local linear embedding, Hessian eigenmaps, and t-SNE, they only provide the high to the low dimensional mapping. And that's actually not what we need here at all. We only need the low to the high dimensional mapping. So there are a variety of techniques that allow you to do that, like self-organizing maps, generative topographic mapping, etc. We found that autoencoders, and in particular the decoder, is a very effective way of doing this, largely due to some of the software support that we now have for that. So if you're not familiar with autoencoders, I expect most people here have at least heard of them. It's a pretty simple idea. The idea is you try to copy inputs to outputs over training data through this sort of bottleneck layer, right? This is just a vanilla autoencoder, with the thinking being that it's an unsupervised method. So if I can successfully copy inputs to outputs, then I've learned some compression of my data. And in our example, our use case, if the data I'm trying to copy correspond to the state vector over all of my training simulations, then you can convince yourself that the decoder actually provides exactly what we're after, which is a parameterization of this manifold, because it provides a mapping from a low dimensional vector to a high dimensional vector, where the image of this mapping spans all of the things that I've seen before, right? So this is the idea, is that we're going to learn an autoencoder and then extract the decoder as this parameterization function that will define our nonlinear manifold. I will explain a little bit later why we're using convolutional autoencoders. We're using those mainly because we're considering for right now sort of Eulerian grids, where we're in CFD, either finite difference or finite volume methods, where there's a strong analogy between that and image data and the way that that data is represented. So if we're using an autoencoder, we take our data just as in POD, and rather than computing in SVD, we're going to introduce an autoencoder architecture and try to copy every column over to a representative column with very low L2 error, right? So we're going to train this network to approximately minimize the Frobenius error, the Frobenius norm of the error between the left and right-hand side matrices. And then after doing that, we're going to define a nonlinear trial manifold by setting our parameterization function equal to this decoder. And the nice thing here is we use the exact same snapshot data as we did previously. We don't need any specialized problem knowledge to do this, and we can just basically do this. So the main challenge here is the fact that we need to train this from scratch. And in AI, the way that they're getting around from scratch training is by essentially transfer learning or domain adaptation methods, where they pre-train networks on similar data on very large data sets like ImageNet. And then for novel problems, they kind of retrain maybe the last layer or the last few layers for the new problem. So in physics, computational physics, we are not at that late level of maturity yet. And what I'm hoping our community can eventually do over time is build up databases of canonical sort of data sets that we can pre-train architectures such as this, such that for new applications, we can apply these sort of domain adaptation or transfer learning ideas to avoid purely from scratch training. But right now we're in the early stages. So everything that we're going to learn here is from scratch, meaning that we need to understand and develop our own architectures, our own initialization schemes. And it's quite difficult for us right now, right? Okay, so to return back to this this thing that I showed earlier, if I look at my manifold ROM methods, and I now know that my G function is provided by a decoder learned from deep learning methods, then what we see is that that the model that I'm using satisfies residual minimization, but we're actually directly integrating deep learning predictions with our computational physics codes. And so what this means is we're basically hooking up PyTorch directly into our numerical solvers that characterize all of our computational physics codes. And this is a pretty interesting sort of way of using deep learning. And so unlike some of the work that great work that Nathan and Steve have done, that's purely data driven, we actually are always kind of tied to this computational physics code, right? That comes with some disadvantages. It's not as easy to implement as a purely black box data driven approach might be. But the main advantage we have is, as I'll get to later on, rigorous error quantification, control of the error, and the ability to exactly enforce things like conservation, which is the subject of the next part of the talk. Anyway, before getting into that, I want to just show a few results that we have generated on 1D burgers and 2D reacting flow, which are sort of academic examples that kind of prove the main idea. We're using convolutional autoencoders, as I alluded to earlier, because it's laid out in a very similar way to image data, where we have a set of data points. In this case, we're considering regular grids with some number of channels. Instead of RGB channels, we have the number of variables that characterize our problem, basically the solution vector itself. And so by using these convolutional architectures, we can bake in things like translational equivariance, which means intuitively, if we have a shock moving through the domain, we can actually capture that shock because it's a translational invariant property of the flow. So basically, these convolutional autoencoders have the right inductive biases for advection dominated problems represented on an Eulerian grid. And as I mentioned, this decoder is what we're going to use to define our manifold. Okay, so let's just zoom in on a very simple instance. I'm not even going to solve a ROM now. I'm just going to do an L2 projection of the solution manifold onto both a POD basis and an autoencoder manifold. And so the leftmost column here is the full order model. We see it's just a simple one-dimensional shock in Burger's case. I'm going to repeat the simulation over and over just so you can see this. If I pick a POD basis of dimension 3, and in this case, the real manifold is of dimension 3 because I have two parameters that are varying, you see what you would expect, right? Because I'm using a linear subspace, I get very, very poor reconstruction of the solution. On the top, I'm plotting what this looks like in generalized coordinate space, x hat 1, 2, and 3. And so, yeah, the reconstruction on the bottom looks very bad, which is what you would expect, again, if you're familiar with model reduction. So let's do the exact same thing, but now with the autoencoder manifold. I'm going to project onto the manifold in the exact same way. I'm going to use the same dimension and the same training data. Then we get this reconstruction. And so when I first saw this result for my postdoc, I didn't believe the results because it's, as a model reduction researcher, you're used to requiring a large number of generalized coordinates to represent advection dominated problems. But because of the inductive biases baked into our architecture, namely translational equivariance, we're able to capture this moving shock with only 3 generalized coordinates, which is pretty amazing. And so hopefully this convinces you of the reason we want to pursue general nonlinear methods. There's no way you could achieve this level of predictive accuracy with any of the methods that I mentioned earlier for representing nonlinear manifolds. So now let's get into an actual reduced order model. I'm going to have both examples as columns here: full order model, then the classical POD LSPG ROM of dimension 5. And again, as you expect, because we have advection phenomena here, we get very poor performance of the ROM of dimension 5, despite the fact that each of these underlying manifolds is of dimension 3. But now if I apply my manifold LSPG ROM of the same dimension, I get negligible errors, sub 1% errors in if I now plot the projection of the solution manifold onto the autoencoder manifold, as opposed to the subspace, what we see are these black dots here. And what we get here is this result that we're after, which is that the autoencoder manifold yields much lower errors than we get even for the theoretically optimal linear subspace. And on the leftmost case, you see that for P equal to the underlying manifold dimension, we get sub 0.1% errors in the projection. If we solve this LSPG model over this manifold, we get the errors shown in pink here, which are also extremely low and better than even the theoretically optimal linear subspace at the same dimension. And so hopefully this convinces you that we are able to break this and overcome this classical barrier that's really prevented linear subspace methods from being effective on advection problems. Yeah, and if I plot now the manifold Galerkin method, that yields these blue squares. we see that, at least in the Burger's case, manifold LSPG does much better, even with the same data and same manifold. And that's likely due to this this a posteriori error analysis result that I showed earlier, where LSPG is minimizing sequentially the error bound. Okay, so that is the end of section 1. Section 2, I'm now going to discuss how we enforce physical properties in our model reduction process. I'm going to focus on finite volume methods applied to conservation laws. So this was my original mathematical formulation. We consider the high fidelity model to be just an ODE system. But if we are going to use a finite volume scheme, we basically derive this ODE from the integral form of the conservation law itself. And so if you're familiar with this, the main idea is we decompose physical space into a set of control volumes, and we explicitly enforce conservation over each of these volumes. And so in this case, each element of the state vector corresponds to the average value of a conserved variable over a control volume. Each element of the velocity corresponds to the flux and source terms of that conserved quantity over that volume. And as a result, the time continuous residual represents the rate of violation of conservation of a variable in a control volume. If we apply time integration from, say, an atom scheme, what we obtain is this result here, which basically the intuition is that each time discrete residual element tells us how much we're violating conservation of some variable in some control volume over some finite time step. And so the name of the game here is, because the high fidelity model sets the residuals to 0, the high fidelity model is enforcing conservation. And that's the intrinsic structure that's enforced by finite volume schemes. So with this interpretation in mind, let's go back to our manifold, Galerkin, and LSPG approximations, right? And so we see that we're minimizing these the L2 norm of these two residuals. And so what this means for conservation for control volume schemes is that we're actually minimizing either the rate of conservation violation or the amount of conservation violation over a finite time step. And because in both of these cases, we cannot guarantee a zero objective function value, we are not explicitly enforcing conservation, right? So we can get actually spurious generation or dissipation of quantities that should be conserved with both of these methods. And so the way that we're going to overcome this is by introducing equality constraints that explicitly enforce conservation. And so you might think to yourself, okay, if you're explicitly enforcing conservation over the original mesh, that's exactly the same as the high fidelity model, and that's an unsolvable problem because it's overdetermined. And you'd be right. And so the way that we get around this is not by enforcing conservation over every control volume. We enforce it over subdomains that we define. The bottom here just is a cartoon of like how you might define different numbers of subdomains and enforce conservation over those. In the most general case is that we enforce only one set of constraints, which is global conservation on the bottom right. So in that case, if we're just enforcing global conservation, then we only introduce, let's say, 5 additional constraints in this formulation corresponding to all 5 conserved variables in like a 3-dimensional Navier-Stokes, for example. And so the idea here again is that we can minimize the L2 norm of the residuals subject to conservation exactly holding over some subset of the problem. And so our paper on this gets into a lot more detail on these approaches, including how do we hyper-reduce the constraints, what are sufficient conditions for feasibility, conditions under which these are equivalent, error bounds, etc. And I'll just briefly mention this error bound result, which is kind of interesting. So one result that we prove here is that the error in the conserved quantities computed with either conservative or Galerkin or LSPG can be bounded as follows. And basically what this means is that if we're doing global conservation enforcement, then because the error depends only on the velocity error on the decomposed mesh, without any source term, and we enforce global conservation, the only error we get in our quantities is the error in the flux along the boundary. And so what we observe empirically is that we get much better preservation of globally conserved quantities with this kind of approach. So I'll return very briefly. So yeah, we have a lot of results on this, but I'll just return briefly to this previous example, just give you some intuition. This is the Burger's case. This is what we get without any conservation enforcement. So the autoencoder on the far right with LSPG looks good. It's like 0.5% solution error, but we do get some violation of conservation, namely 1% error in the conservation law globally. So if we now introduce these constraints to the projection scheme, we get visually similar results, but actually even in the POD case, we get machine zero error in the amount that we're violating global conservation, which we anticipate will lead to much better performance and stability over long time integration cases that we expect in turbulence, for example. So here again are these models. One question you might ask yourself too is how easy is it to actually solve these problems? We're using SQP methods in both cases. And because we're using Gauss-Newton methods for the unconstrained versions of this, it's actually the exact same structure if you use an SQP solver, and the additional cost is almost negligible when you do global conservation. So okay, how do we interpret this? So basically, again, we're integrating computational physics with deep learning. From the AI community's viewpoint, what we're doing is learning a latent dynamics model. That's actually a pretty hot area in AI, but it's not purely data driven, as I mentioned before, right? So we're not just like getting a bunch of data and then generating a dynamics model via like an LSTM or some kind of recurrent neural network. We're actually generating the dynamics by putting that approximation back into our real physics code and computing optimal projections with respect to the true misfit of the physics with respect to the approximation. We use AutoGrad to compute the decoder Jacobian, which is implemented in all modern deep learning toolkits like PyTorch. And we have some ongoing work here, and I'll call out briefly that we have a extension of all of this to a general optimization formulation that allows us to preserve general physical properties and model reduction. And that was worked on with my collaborators Alexander Schein and Matthew Czar. So that paper kind of lays out, it's just accepted to IJ&ME, how we enforce both arbitrary kinematic and dynamic properties in model reduction via a constrained optimization projection formulation. Okay, so now I'm going to get into this last topic very briefly. It's a little bit easier to get your head around, so it should be a little bit faster. Okay, so let's say we run our fast model and it runs very quickly. And I want to understand how accurate my reduced order model was, right? So I can return to this error bound that I derived, and our community has derived a whole host of these bounds. And one can compute this because it's a computable a posteriori bound. I just need to compute the L2 norm of the residual at every point in time, and then I can assemble this bound after the fact. And so the question is, can we use these bounds for pragmatic error estimation? And so the way that you can answer that is if you actually derive out this recurrence and come up with global, these are local bounds, global bounds, what you see is that the stability constants in the global bound actually grow exponentially in time. And that's not surprising because these error bounds are based on the worst case scenario at every time instance, right? So you're assuming the worst case thing can happen, and then you're accumulating those errors over time, which is exponential growth, right? And so it's not surprising that we get these exponentially growing stability constants. And it's also a deterministic bound, and most of the decision-making that we do is actually stochastic in nature, right? So it'd be much more pragmatic, I would argue in many cases, to have a probability distribution over the ROM error that's rooted in statistical analysis. And that's the main idea that we're going to pursue here. And so here's just a kind of a very simple case that gives you intuition into our approach. So here's this is actually on a parameterized diffusion problem. If I plot just the residual or error bound versus the real error in this example, the x-axis is easily computable. The y-axis is what's not easily computable because it requires simulating the high fidelity model. We see that ROMs are generating quantities that are residual based that are highly informative of the error. And so from an ML viewpoint, we view these as good features that are useful for generating a statistical model of the error. And so the main idea of this line of work is that we have, I think, a sequence of 3 or 4 papers now where we apply machine learning regression techniques with statistical rigor that generate a mapping from these computable residual based quantities to a random variable for the error whose statistics are actually representative of the uncertainty in our predictions. And we call these machine learning error models. So to build the architectures that we want to use to get as much predictive accuracy out of these models as possible, let's appeal to some of the error analysis that we've done and understand what attributes that the ROM error might have that we could bake into our inductive biases. So here's the global state space error bound I showed earlier. And we're going to extract a few sort of qualitative features of this bound to bake into our model. So number one, what we see is that the error bound depends on non-local quantities in time. This is intuitive because an error that was incurred at time step 1 could accumulate and compound and yield an error at time step 1000, right? So that's the first thing that we observe, is that non-local quantities in time affect the error. Number 2 is we have dependence on the residual, which is obvious sort of if you're familiar with error analysis techniques where you can bound the error from above and below by the residual multiplied by respective stability or coercivity constants. And so what we're going to do is actually build a regression model that reflects these 2 inductive biases. And we're going to have our regression model be composed of two additive terms. This is sort of a choice we make. The first is a deterministic term, and the second is an additive stochastic term. Moving forward, this is not strictly necessary. We could bake it all into one stochastic thing, but for just to facilitate training, we're going to adopt this approach. And the regression function that we're going to build in is basically a classical sort of recurrent architecture where we have some latent variables, H, that are used. So basically this first equation here describes like how we characterize the error at every time step. And the second expression characterizes dynamics for the latent variables that allow us to preserve memory and effects over long time histories. So these latent variables, as I mentioned, are essential for capturing feature one above, or quality one above, which is the needing to capture non-local dependencies. And the features that we're going to use are these things that we know have high mutual information with respect to the error in the ROM, which are these residual-based quantities that are cheaply computable and we know are relevant to error predictions. And so the main idea there is basically we're going to subsample the residual in the domain, which we can already easily do because that's part of our ROM simulation anyhow. And this general formulation encompasses a wide range of time series modeling methods, all the way from like classical autoregressive with exogenous input methods, all the way to LSTM, GRU, RNN type architectures. So for LSTM, if you're not familiar, this is the main idea of like how you would instantiate this model for an LSTM architecture. You see, we have these exogenous inputs coming in from the bottom. These are these residual-based error indicators that we can cheaply compute. We have this memory that's persisting via these like sort of the cell state and in the memory state that's getting propagated throughout the network that preserves memory over arbitrarily long time instances. And then this red term at the top is what we're predicting. And F is just the function that generates that from our hidden variables. Yeah, so how would this work in our three-step process? So we've already solved the full order model. We then go back and solve our cheap ROM, and we collect feature response pairs, right? This is a supervised learning approach. So we collect the thing that we're trying to predict, which is the response, and then the feature, which is what we're going to try to predict that from. We do that at all the points that we already have a high fidelity simulation data. And then we just turn the crank on like common machine learning approach, which isn't all that interesting, right? We divide into training and test. We use cross-validation, et cetera. And then the way that we construct our noise model is just by the sample variance on the test data. It's just a very simple initial pass at characterizing uncertainty. So in our reduction or inference stage, what we do is we run our reduced order model. Those generate these cheaply computable features that we put into our regression model. That will then output this machine learning error model, which allows us to append some statistical model for the ROM error on what we computed above, such that at the end of the day, what we get is an approximation of the high fidelity model quantity of interest that we care about, that whose statistics represent our uncertainty in that quantity based on our ROM prediction, right? So this is a way of making statistically rigorous predictions of our quantities of interest using computations that are all sort of n-independent, have incurred n-independent operation count. So we did a pretty extensive study here. The number of each row here is a different kind of regression method, going from sort of classical all the way to modern deep learning methods. And each column here corresponds to a different set of feature combinations. And I'm plotting here the FVU value. And so if you get down into minus 0.2, that means that we're the R squared is basically 0.99, which is extremely good. We're explaining almost all the variance in our model with that. So the first thing we see is that just empirically, these RNN and LSTM methods are very accurate. They're the best performing methods. So we're not just using deep learning because it's cool. And then what we also see is that we only need really 7 residual samples to get very good accuracy, which is extremely impressive in my opinion, because we don't need to do calculations anywhere outside of our existing sample mesh. So I think I'm completely out of time, but I'd be happy to take any questions if people want to stick around a little bit.
Thank you very much, Dr. Carlberg. That was an excellent talk. If you have a few minutes, I believe there's a few questions,
Sure.
but that's entirely up to you.
Yeah, I definitely have time.
Okay, so there's one coming from the chat here. Okay, so the first one that came from the chat was, I was wondering, what do you think about using attention-based models to capture dynamics?
Oh, that's a very, okay. Sorry, let me just make sure I got the question right. Attention-based models for what? Capture dynamics. Oh, I love this question. This is this is getting into some research I actually want to do at UW. Yeah, I think it's a very cool idea. The thinking that I have right now on that is basically for space-time projection, you could imagine these self-attention mechanisms or transformers as a really cool way of doing space-time compression. So we've done some of this with with sort of multilinear algebraic methods. So tensor decompositions to compress both space and time. That's work I did with Young Soo Choi. But I think some of these more modern methods for doing that, you could imagine different ways of dealing with the temporal dimension. I was going to talk about this actually in some other version of this talk, but I decided not to cover this. But yeah, you could imagine either space-time autoencoders as a way of dealing with time, or more interestingly, what you're alluding to, which is like self-attention architectures. It's interesting. It's been proven out very well in natural language processing. And more recently, actually, Facebook AI just released actually a video model that uses transformers for video understanding, which is the first of its kind there. So I think it'd be very interesting for our community to look into self-attention for space-time model reduction for sure. I think that's a very good idea.
Great. And so another one coming from the chat is for the nonlinear LSPG, can we infer how nonlinear the projection manifold is from the learned decoder? And will this tell us anything about the priorities of the equation we are trying to solve? Oh, the properties of the equation. Sorry.
Yeah, I see the question there. I haven't ever tried to do this, but I mean, you could easily do something where you maybe like collect samples of the tangent space of the manifold, right? You could imagine sampling the manifold, collecting the tangent space, and then doing some kind of like cosine similarity between those like subspaces that you're learning to get some average curvature of it. Or you could maybe even compute the curvature directly by computing the second order gradients of the manifold at different points. So yeah, I think there are ways of characterizing the curvature and deviation from the linear subspace. I don't think it tells us anything about. So the interesting thing here is you can have actually a linear equation, but nonlinear manifolds underpinning it, right? So like linear Berger's equation is a good example of a set of linear dynamics that yields a nonlinear solution manifold. You could also have nonlinear dynamics that yield a linear solution manifold, like a nonlinear diffusion problem. So from that viewpoint, yeah, like the nonlinearity of the manifold tells you about the kinematic properties of your solution manifold, but not necessarily how nonlinear the operators themselves are. Yeah, you could also do what we did here, where you actually compute the optimal linear subspace and the nonlinear manifold and look at the projection errors as you increase the dimensionality.
Great. And so Jake actually in the chat here read my mind, because this was the same question I was going to ask you. It's so are you assuming that you have a constant time step when you're doing the data aggregation? And then, if you are, is this a restrictive or a realistic assumption?
Yeah, we don't assume anything about uniformity of time step at all. In this talk, I just like didn't put an index on the time step size because that becomes overwhelming. But yeah, all of our papers, you just have an arbitrary time step size. I will say that, and I didn't have time to talk about this, in one of our paper from 2017, we show that the time step selection is a very interesting quantity with LSPG, because we're doing time discrete minimization. So effectively, we're minimizing over the time window that associates with the discretization step, right? And so there's a weird coupling between the approximation and the discretization. And so that is sort of why, and I'll pull this reference back up, this paper that that Eric and I recently did tries to get at that issue where you decouple the projection time window from the discretization step you take. And so if you're interested there, this sort of last, I don't have the full reference there, but Parrish and Carlberg from 2019, we actually like completely decouple the time step size from the projection time window to generalize this approach, which is kind of obviously the right thing to do, right? There's no real reason to conflate the time step for discretization with the time step for projection.
Very nice. Great. Okay, so another one is I'm wondering, what is the performance of the LSPG in more complex problems, say the extreme scale applications mentioned on your background page? So I think they're referring to some of the turbulent flow problems.
Yeah. So so at my previous employer there, so the example I showed there was pretty large. I mean, that's 1 million degrees of freedom. It's not like massively large scale. They have published stuff more recently. I'm an author on some of it, where they are pushing the boundaries of that up to like 10 million degrees of freedom. And what we're seeing in turbulent flows is the only way to make it work really is if you have a periodic flow. This is all with linear subspaces, right? If you have a periodic flow, you collect enough data and then you like forecast in the future. That has nothing to do really with the fact that it's a large scale problem. It's that it's a chaotic problem, right? That it's turbulence. And so, yeah, sort of the scale, the number of degrees of freedom in your high fidelity model doesn't affect the sort of the viability of model reduction. It has to do with the dynamical system properties themselves. So for these chaotic problems, it's really hard to do parameter variation. You have to do some kind of least square shadowing approach to get a like to generate a smooth solution manifold, like so like what Chi-Chi Wang and Patrick Blonigan have done, to get a smooth underlying manifold from that chaotic problem, and then apply model reduction to that smoothed out manifold. But yeah, I think there's been quite a bit of work that has come out on like actually trying this on extreme scale up to like 10 million degrees of freedom type problems.
Very nice, very nice. And so the current, or one of the last questions in the chat here is, would it be beneficial to use medium level fidelity models, especially for the last part with error estimation? So in a similar, in a fashion similar to Runge-Kutta methods that use two schemes to estimate the error.
Yeah, I think that's a good idea. I mean, so there's a whole sort of orthogonal research area to this that, for example, Ben Perestorfer and Karen Wilcox have done a lot of great work in, of like multi-level methods, and Mike Eldred at Sandia has done a lot of this work too, where you basically try to make statements about problems by leveraging a whole hierarchy of models of different fidelity. Our take on this is that this is one model in that hierarchy, right? So what the goal of my research is to do is to say, okay, whatever hierarchical approach that you want to adopt, my job is to build the best surrogate model to plug into that, right? So I want to make a model that's as accurate and as fast as possible to be like Pareto dominant to like some of these like coarse models that you're describing, right? So why would you use a coarse model when this model would be both faster and more accurate, right? And so the idea here is basically to come up with the best surrogate model that you could to sort of replace what you might call like naive approaches, and they're not naive, but it's like simpler approaches that are like coarsening the mesh, removing physics, and so on.
So I thought that was the last question in the chat, but a few more have come in. It's always a good thing. That means people actually paid attention and enjoyed your talk, but we don't want to take too much of your time. So
yeah, maybe I could take like one more question, and then I probably should run. But
okay, great. So I'll just do it in the linear order that it came in. So there's no preference being made here. But so the question is, how do you do hyper reduction in the nonlinear setting? I imagine that if you are trying to find I think this is supposed to be semi-norm that approximates the original norm, you still need a large number of points because of the same Kolmogorov width issues.
Yeah, so there's sort of two parts to the answer there. One is like, how do you do hyperreduction at all? And the second is like, will hyperreduction work, right? The way that you do it is you need to make sure that your architecture will preserve sparsity through the layers, right? Because like what wouldn't work is if you have a fully connected decoder and then you want to just sample a small number of the outputs, and then like the layer upstream of that would just kind of mix everything together and you would get no savings upstream. And so fully connected architectures don't work. What does work really well are the convolutional things that we're describing here, because that's effectively the same as using basically sparse layers going upstream, where like the receptive field of the external of each area is like finite. And so basically by using these convolutional architectures, maybe with being a little bit careful about stride and things like that, you can ensure that sampling a small number of points will incur an operation count that's independent of the original degrees of freedom. So you do have to be careful about your decoder architecture to ensure that sampling the output will yield an actual cost reduction. That's a good point. Regarding the hyper reduction itself, there's actually no issue at all compared to the classical method about like Kolmogorov width limitations or anything like that. Basically, all we're trying to do is approximate the norm, and that is completely independent of what, if you look at like the expression, but let's just take on this current slide that bottom left equation, right? So the way that I approximate the norm is independent of the space over which I'm searching for solutions in V, right? So I can have any kind of approximate solution there. The point is that over that space, I need to then approximate the norm. So I don't see any reason why we couldn't use the typical methods for approximating the L2 norm of the residual. So right now we're thinking about sort of just random sampling, as well as sort of weighted quadrature approaches similar to what Farhat and Doug James have done in the past for like their ECSW or sparse cubature methods. But I think those are actually two different things. Like the Kolmogorov width characterizes the solution space. And then what we're doing here is just trying to approximate the L2 norm of the residual. Those are very different concepts that I don't think are too related to one another.
Great. Okay, so that's all the time that we have for questions. So thank you very much, Dr. Carlberg.
Thank you. Yeah, thanks so much. I really appreciate it. And feel free to email me with questions, or if anyone wants to chat more, it'd be great.
Wonderful. Yes, thank you very much for the great talk.
Thanks.
And for those of us that have stuck around in the chat, I just remind you, we're back on our regular schedule next week. So we have a talk again next Friday at 9 a.m. Pacific time. So we hope to see everybody back again next week.